Experiment 15, chemical equilibrium and LeChatelier's principle, is not something that is extensively covered in most 127 lecture classes, but it is something with which you interact every day and is definitely a topic worth exploring experimentally. So here's two practical situations where equilibria and LeChatelier's principle can come into play. First, number one, imagine you've been poisoned by carbon monoxide. How can you most effectively not die? Replace the carbon monoxide on your hemoglobin with oxygen. Carbon monoxide sticks to hemoglobin better than oxygen, in fact, and so it requires high concentration of oxygen to flush it out of your body. Why does that work? An equilibrium situation could be argued to be at play. And then, as many of you have experienced perhaps, and certainly it gets even more fun as you get older, why is it so difficult to lose or gain weight? Your body maintains a relatively constant weight even though you're putting stuff into your body, eating and breathing in every day, and getting stuff out of your body, excreting and breathing out every day. What's going on there? Your body is really good at maintaining an equilibrium. Equilibrium reactions are reactions that go both ways. When we first introduce reactions, typically there's an arrow going from the left side, the reactant side, to the right, product side. But in an equilibrium reaction, the arrow goes both ways because the reaction doesn't just finish. It doesn't go to completion. You have appreciable amounts of both left side reactants and right side products present. And there's a little terminology that goes along with it. The forward reaction is the left to right reaction. The reverse reaction is the right to left reaction. But typically when we speak about these things, we still call the things on the left reactants and the things on the right products. Although in the reverse reaction, these would be your reactants on the right, and this would be your product on the left for the reverse reaction. It's going both ways. Equilibrium technically happens when the reactants forming products occurs at the same rate as the products forming reactants. When the forward reaction rate and the reverse reaction rate are the same, that is the definition of equilibrium. That has absolutely nothing to do with how much reactant and products are present. There may be way more reactants, there may be way more products, there may be relatively equal amounts of both. All of that can be studied in the lab and mathematically, theoretically, but it has nothing to do with equilibrium, that you have more of one than the other, or that they have to be equal. That's not true, okay? You do not need equal amounts for there to be an equilibrium. It's that reactants are forming products, products are forming reactants at the same rate so that you have a constant amount of reactants and a constant amount of products. But the specific molecules or compounds involved need not be constant. These are breaking apart to form these. These are combining to form those. Okay? You have constant amounts of each, but the specific molecules are not constant. The reactions are occurring forward and back. They are incomplete reactions because you have some reactants and some products, maybe equal amounts, maybe more of one than the other, at equilibrium. We can measure how much reactant versus product we have with something called the equilibrium constant, which we generally do not calculate in 127 lecture. But you can see based on the equation that it's product meaning multiplied by, it's the product of the product concentrations is on top, the numerator, and the product of the reactant concentrations, the left side of the equation, compounds, on the denominator, on the bottom. The exponents are the coefficients from the balanced chemical equation. So if K is very, very big, that means that the top has to be bigger than the bottom. If K is very, very, very small, that would mean that the bottom would be bigger than the top. If K is very large, top is bigger, that means it's mostly products, it's mostly forward reaction, it's mostly right side that's existing at equilibrium. If K is very, very, very small, like 0.0001 or something like that, then it's mostly reactants, mostly left side that is present at equilibrium. Again, we don't calculate these very much, and it's not involved at all in the lab. but you can measure the position of equilibrium. Is it relatively equal amounts? K will be close to 1. Is it mostly products? K will be very big. Is it mostly reactants? Left side, K will be very small. K can never be negative because it's all concentrations in here, and you can't have negative concentration. LeChatelier's principle, or LeChatelier's principle, says that when you stress a reaction at equilibrium, the system will respond to minimize the stress. Fine. What does that mean? Stress can be adding a reactant or a product or removing a reactant or a product. And when you have endothermic or exothermic reactions, where heat can be treated as a reactant, if it's an endothermic reaction, or a product, if it's an exothermic reaction, then changing the temperature is effectively adding or removing a product or a reactant. Technically it's effectively adding a reactant or a product and not removing. Although if you're lowering the temperature, you could argue it either way. So changing the temperature, if you're treating heat as a reactant or a product, which it arguably is in an exothermic or an endothermic reaction, then it's the same as adding a reactant or adding a product, and the equilibrium system will shift after you've made that change. How can you predict what that looks like? I like using little arrows, that if you add a reactant or remove a product, that it shifts to the right. You're just following the direction of the arrows. If you're adding a product or removing a reactant, just follow the arrows. It shifts to the left. Now think about what this means for a exothermic or an endothermic reaction. First of all, we have to remember, is heat a reactant or a product? Or is it on the reactant side or the product side for an exothermic reaction? Conversely, is heat on the reactant side or the product side for an endothermic reaction? Now, given what you've said, if you increase the temperature of an exothermic reaction, which way should the reactions shift? If you decrease the temperature for an exothermic reaction, which way should the reaction shift? And then the others would be opposite. If you increase the temperature for an endothermic reaction, which way should it shift? If you decrease the temperature for an endothermic reaction, which way should it shift? Well, this is one of the things we'll explore in part 3 of the lab this week, is changing the temperature. In the other two parts, part 1 and part 2, we'll add or remove reactants or products. So here's a practice that we can do with your instructor or with the video if this is a play pause it exercise for your class. Here's another reaction that SO2 combines with O2 to form SO3 and heat. So is this an exothermic or an endothermic reaction with heat on the product side? Exothermic. So if we add oxygen, which way is the reaction going to shift to minimize that stress? If we add heat, increasing the temperature, which way is the reaction going to shift? If we add heat, which way is it going to shift? If we remove SO2, which way is the reaction going to shift? If we remove SO2. What about if we add SO3? If we add SO3, which way is it going to shift? Here's the reaction that's involved in the lab. And all of the reactions that are involved in the lab this week are incredibly complex. They use transition metals, which we fundamentally ignore in Chemistry 127 because transition metals, generally speaking, don't play by the rules. They form complex ions and do other complex chemistry that you really don't study, honestly, until graduate school. I was an inorganic chemist in graduate school, and that's when I started studying this type of reaction. I didn't do it even as an undergraduate, even after taking 6 years of chemistry and 3.5 years to be a chemistry major. So this is the first reaction that we're looking at. If you have iron 3 ions as iron 3 nitrate, it looks yellow in solution. But when you form a complex ion with iron 3 FeSCN2+, that is blood red in color. And so if we add reactants or if we remove products, or conversely, if we add products or remove reactants, we can get our shift to the right or shift to the left following our arrows appropriately, and our solution will change color. It'll either get more yellow or more red, depending on whether it's shifting to the left, yellow, or to the right, red. In part 2, it's more complex ion chemistry. If you have copper 2 ions and add ammonia, you form the complex copper tetraammonium 2+ ion. And that's a different color. It's a really, really deep royal blue, as opposed to copper 2 ions in solution are just a turquoise light blue, as you saw with the spectrophotometry lab, the Beer's Law lab. By adding ammonia or removing ammonia, by adding acid, reacting this acid with the base would remove ammonia, we can get this equilibrium to shift left, light blue, or shift right, royal blue. In part 3 of the lab, more complex ion chemistry, cobalt hexaequo ions look pink in solution, but cobalt 2 tetrachloride ions in solution, the complex ion COCl4 2-, still has cobalt +2 ions as part of this complex ion, is a purple-blue color. By adding one of our reactants, chloride, or by adding one of our reactants, heat, or taking one of our reactants away, heat, increasing or decreasing the temperature, we can influence this endothermic equilibrium to shift left or shift right. So in part 3, we're not really messing with our reactants. We are messing with the temperature of our reaction, which, again, arguably we could say that heat is a reactant here. And so we'll see by changing the temperature what the color of our solution is, and see if that will tell us, have we shifted left or have we shifted right? On your data sheet, in your observation column, you're going to write down the color of the solution in each case. In part 2, you can note how much acid or base you add, just so that you have kind of a record of it. They're the same concentration, so if you add equal number of drops, you should have added equal amounts of acid or base. And in your conclusion column, which I guess we could really say is a result column rather than a conclusion column, you can say which way the reaction shifted, left or right. Practically speaking, do make sure that in part 3 you understand that you're starting with an equilibrium mixture of the pink and the blue. So it will look somewhere in the middle at the beginning, and you'll shift it further to the left or further to the right, depending on how much is present at equilibrium in the starting mixture. Keep in mind in part 3 also what side of the reaction heat is on, and what that means when you raise or lower the temperature. And as always, mistakes are not valid sources of error, so you cannot say that I messed up in the video if you're doing this as a video lab, or if you're doing it in person, you can't say that you messed up either. If you mess up, repeat that part of the experiment and get good data. Enjoy experiment 15, chemical equilibrium, and LeChatelier's principle.